Welcome back to our class. Don't forget to subscribe if it is your first time to visit our channel. So today we are looking at the standard electrode potential. The reactivity series is a list of substances which are arranged in order of their ability to act as reducing agents or oxidizing agents. So now we are going to look at which one is a strong reducing agent, which one is a weak reducing agent. And then if you know that, then you know how to interpret the reactivity series, then you will be able to know which one is going to be on the cathode, which one is going to be on the anode. So we are saying that a table of standard reduction potential can be used to, number one, we're going to look at that table and interpret it better. Number one, identifying the oxidizing and reducing agents. So we are able to know that this is a strong reducing agent, this is a strong oxidizing agent. Number two, writing a balanced redox reaction equation. You can be able to write this, predict whether the reaction is a redox, yes, is taking place spontaneously or not. So you can predict whether this redox reaction is spontaneous or it's not spontaneous. It can continue without an external battery. It can continue without an external source, power source, or it can't continue without an external power source. That's the meaning of spontaneous. And then you're saying that you can calculate the EMF, electromotive force, that is EMF, of this cell. So basically, this is the formula you are going to be using. This is the formula you're going to be using. Electrode potential of the cell is equal to electrode potential of the cathode. Remember, the anode is the negative terminal. So the positive terminal minus the negative terminal. So we need to know which one is supposed to be at the cathode and which one is supposed to be at the anode. Or you can use this equation. The electrode potential of a cell is equal to electrode potential of the oxidizing agent minus electrode potential of reducing agent. So you can use this, and then this is the formula you're going to be using so that we can calculate. But the problem is, how do we get this and how do we get this? So we need to understand how do we get this figure and how do we get this figure so that we can substitute in this formula, and then we'll be able to write the electrode potential of that cell. Standard hydrogen potential. Let's look at standard hydrogen potential. Why do we start with the standard hydrogen potential? Because hydrogen is regarded to be the benchmark, is the one which we compare to. We compare to hydrogen. Whatever we do, we compare it to hydrogen. So it's the standard. Above it, then it means that the cell can continue. Below it, it means that the cell cannot continue. So we are saying that hydrogen gas, or what you call the hydrozonium ion, electrode has been chosen to be a standard half cell. So we are saying that it's regarded as the standard half cell. We compare to hydrogen. Basically, what happens is, if you look at this, you have hydrochloric acid. The reason why you have hydrochloric acid is just to increase the conductivity. Then you have platinum. Platinum or electrode has been coated with platinum. Yes. Why do we put a platinum here? Why? Because hydrogen is a gas. So we need something where hydrogen is supposed to go to so that it can react. So this platinum is just used so that it provides a surface area for this hydrogen to react. So it comes like this to platinum. When it reaches platinum, then it can react from here. So the reason why this one is there is just to increase the surface area or to give the ground for hydrogen to react. So we are saying that the standard hydrogen electrode is a redox reaction. It means that it can have oxidation and reduction, which form a basis of the thermodynamics scale of oxidation reduction potential. So it means that whatever we are going to be doing, we are going to be relating it to hydrogen. So we regard this one to be 0, 0. You start from 0, 0. When you are numbering or you are counting, you start from 0. 1, 2, 3, 4 until whatever you want to reach. Or you start from 0 and then you go to negative. Negative 1, negative 2, negative 3. So in this case, hydrogen is the standard where we are supposed to start from. Oh, here is the standard electrode potential. You need to know. You see, hydrogen is here in the middle. Yes. Above it, it means that this one is more reactive than hydrogen. Below it, it means that it is less reactive than hydrogen. So if it is above it, yes, if it is more reactive, then it means that these ones are going to be anodes to produce electrons, whereby hydrogen is going to receive them. Below them, below hydrogen, it means that these ones are less reactive. Then it shows that hydrogen is going to be at the anode, which means that hydrogen is going to be the negative terminal. So hydrogen will be dissolving to produce electrons which are going to be accepted by this. Now, look at this. If you are comparing two of them, for example, calcium and copper, yes? Calcium is at a top level, while copper at a lower level. The one which is at a top level is supposed to be the anode. You must know that. It's supposed to be the anode. And then the one which is at lower level, is supposed to be the cathode. Remember, anode is the negative. And then the cathode is the positive. So the anode will dissolve to give electrons, and then which are being accepted by the cathode. So we shall say that the anode is what? Is oxidized. Therefore, it's a strong reducing agent. So that's why you see that as you go up, the reducing agent increases the strength. So as you go up, it becomes more strong. It becomes more reactive. It becomes more easily release the electrons. It can easily release the what? The electrons. Or electrons can be easily released. So it becomes a strong reducing agent. A strong reducing agent is supposed to be at the anode, yes? And then a weak reducing agent is supposed to be at the cathode. Why? Because this one is positive, this one is negative. So this one gives electrons to this. So now we are going to compare copper, yes, copper with hydrogen. So I will come here and say, hydrogen is here, yes? Copper, you have copper 2 to copper 1. It's not yet fully reduced. The one which is fully reduced is this one. So I have hydrogen and the copper. So which one is going to be at the cathode? Which one is going to be at the anode? We say that the one which is on top is supposed to be the anode. The one which is down is supposed to be the what? The cathode. So now I will say that hydrogen is going to be at the anode. So it's going to become the negative electrode, the negative electrode. And then copper is going to be at the cathode, the positive electrode. What about when I compare hydrogen and zinc? We have seen here that now here hydrogen is at the anode and the copper is at the cathode. What about hydrogen and zinc? You have zinc here and then you have hydrogen here. So it means that zinc is more reactive than hydrogen. Therefore, zinc is going to be at the anode, while hydrogen is going to be at the cathode. You see? So the one which is more reactive must be at the anode. The one which is less reactive must be at the cathode. The one which is on top, even if you don't read this, it's fine. The one which is on top is more reactive. Is easy in releasing electrons. You must have that concept. The one which is on top is easy to release electrons. So this one, it easily releases electrons. You understand? So it becomes the anode. And then the one which is below hydrogen, it becomes the cathode. It means that it's easy in accepting the what? Electrons. So let's go back to determining the standard electrode potential of copper half cell. Here you have the copper half cell. You have hydrogen this side, you have copper this side. We don't know which one is the cathode, we don't know which one is the anode. Now, how do I identify that this is the cathode, this is the anode? This is what you are supposed to do. Hydrogen and the copper. Hydrogen is more reactive than copper. So what does it mean? Hydrogen must be at the anode. Copper must be at the cathode. I go back. I have to find out. So we say that hydrogen is more reactive than copper. So this one becomes my cathode. Why? Because hydrogen is more reactive than copper. And then the one which is more reactive, the one which is above the reactivity series is supposed to be the anode. The one which is below the reactivity series is supposed to be the cathode. This is a negative terminal. This is a positive terminal. Negative terminal give out electrons. Positive terminal receive the electrons. You see? Now I'm going to go to identify which one is a positive, which one is the cathode, which is an anode. Now I have to know which reaction is happening on each. If this is negative terminal, yes, and it gives out electron, so I have to show a reaction here where the electrons are forming. It means that when hydrogen comes, yes, it's gonna react here to form hydrogen ions plus electrons. Yes, these electrons will move to the cathode, where copper is going to receive these electrons, so copper 2 ions, plus these 2 electrons to form copper solid. You see here, hydrogen comes in, yes, it forms hydrogen, hydrogen gas, is supposed to have a gas here, and then hydrogen ions, so it dissolves here, it reacts here at the platinum, and then it forms hydrogen ions, which is aqueous, plus 2 electrons. These 2 electrons, they move. When they move, they come to copper. Here you have copper copper solution. Yes, these copper 2 ions, they accept these electrons, yes, and then forms copper solid. So what is happening? But all this, you have identified it from this. You have identified this from this point, that hydrogen is above, copper is below. So hydrogen becomes the anode, while copper becomes the cathode. How do you write the full reaction equation? Hydrogen, that's before the arrow, plus copper 2 ions, giving me after the arrow 2 hydrogen ions plus copper solid. This is what I'm trying to say. Hydrogen gas, yes, plus copper 2 ions, which is here, giving me hydrogen, 2 hydrogen ions, which is this, plus copper solid. That's it. So before the arrow and then after the arrow. Before the arrow and after the arrow. So it's supposed to be like that. So, and then you cancel out what is similar. Electrons this side, I have electrons this side, I have electrons this side. So I cancel them out. So how do I write the cell notation? How do I write the cell notation? This is the cell net cell reaction. This is the half cell reaction. And then this is the half cell reaction for copper. This is the full when I combine them. What about the cell notation? How do I represent this in the form of equation? So I will start with this. Yes. So I will say that I have with the anode. Yes, when you write the cell notation. I have hydrogen. Yes, the hydrogen. This hydrogen goes to platinum. So I have hydrogen gas, comma, it goes to platinum because this platinum shows that this is just an electrode. But if, okay, I'll explain it. It is showing just an electrode. So this hydrogen, the hydrogen gas, comes to platinum. Yes. When it comes to platinum, it reacts, you see, it reacts to form hydrogen ions. So it reacts to form hydrogen ions. Are you seeing? Which is aqueous. Then I've completed this one. But in between here, we have a salt bridge. Remember I said that the salt bridge is indicated by a double forward slash. So forward slash, then I go to copper. So when these electrons come, they will find the solution here of copper. Yes. So this copper two ions, yes, which is aqueous, yes, it will give me copper solid, which is this. So basically, that's how you're supposed to write it. In this cell notation, we don't balance the equation. You don't put the two. No, you just have to write what is really happening. But in the net cell reaction, we balance. It's supposed to be balanced. That's why you have here only hydrogen ion, and yet here you have two hydrogen ions. Let's look at another example. So we have said that this is zinc. The reaction is talking about zinc, measuring electrode potential of zinc to iron, zinc to iron in the system. All right, what happens? So now I have to know, this side I have hydrogen, this side I have what? I have zinc. Now I don't know which one is the, don't cram, I don't know which one is a cathode, which one is anode. So we have to go back to the reactivity series, and then we see zinc versus hydrogen. Zinc is here, yes, versus hydrogen. Hydrogen is here, yes. So it means that zinc is more reactive than hydrogen. So it means that zinc is going to be the anode, while hydrogen is going to be the cathode. Let's go back. So now if you are saying that now, we have understood that zinc is the anode, is the negative, it's more reactive anode. Which one is on top? Anode. And then the one which is below becomes the cathode. So this one becomes negative. So this one becomes positive. This one becomes negative. So this is anode, this is cathode. This is anode, this is cathode. It means that this one gives electrons to this. So let's interpret. It shows that zinc is going to react, yes, to form zinc ions. Then these two electrons are going to move, yes, to go to hydrogen electrode. You see? Now, what happens? The hydrogen ions, which are in the solution here, yes, are going to accept the two electrons from the zinc to form hydrogen gas. That's how it's supposed to be. We find oxidation. This one is oxidized from zinc, which is 0, to zinc 2 ion. It's oxidized. So it releases electrons. Electrons will travel to this. Now, this one is what? Is now negative. It shows that now it can continue on its own. Yes. This, yes, it means that it's a strong, this one, it shows that is a strong reducing agent. If it is negative, it shows that is a strong reducing agent. If it is positive, it shows that it's a weak reducing agent. So basically, that's it. So how do we write this full cell equation or net cell reaction? So you have, you're supposed to start with the anode, then you end with the cathode. In this case, this is the anode, and then this is the cathode. So let's see. Zinc, yes, which is zinc, this one, for the arrow, plus 2 electrons, plus 2 hydrogen ions, which is this. Electrons have cancelled, giving me hydrogen after the arrow, plus zinc 2, which is after the arrow. That's how you're supposed to write. Cell notation. Remember, you start with the anode. So zinc, which is a solid, yes, is oxidized. Yes, is oxidized, or it dissolves. This electrode dissolves to give zinc 2 ions. So zinc, which is a solid, is oxidized to zinc 2 ions. Yes. So now I don't have anything this side. Then I'm separating this by a short bridge. Slash, yes, when it goes here, these electrons, they will find the ions here, or hydrogen. So it will find the hydrogen ions, yes, it will find the hydrogen ions. When they find hydrogen ions, these electrons will react with the hydrogen ions to form hydrogen gas. So I have hydrogen ions to give me hydrogen gas. And then this is taking place. The hydrogen gas is being produced at this plate or this electrode, which is a platinum. So you see how it's supposed to be. So now the platinum is at the end. So that's how you can write the cell notation. If this was a solid, then I won't need this platinum there. Why? Because I have, maybe if it was copper, then it means that I'll just have to stop here. Why? Because copper is a solid. But if it is a gas and then I use another electrode like platinum, then I have to put the platinum there. Electromotive force of a electrochemical cell. So how do I calculate now this?